This is Chapter 8, Section 4, Conservation of Momentum. The law of conservation of momentum states that in the absence of an external force, the momentum of a system remains unchanged. In order for something to move, we already know this from Newton's second law, something has to act on the object to make it move. We said that forces inside a baseball or a basketball can't move the basketball, therefore they're going to have no force, no effect on the momentum of the basketball. And we also said you can't be part of a system and push from within the system to make something move. Like pushing the dashboard of a car won't make your car move, or sitting on a sailboat blowing on the sail won't make the sailboat move. These are what we call internal forces, and they're in balanced pairs. So in this case, the internal forces are within the system or within the object, so they will cancel out. So that being the case, let's look at a system, a cannon with a cannonball inside of it. Now the momentum before firing it is zero. Both of the things are at rest. The cannonball is not moving, the cannon's not moving. After you fire, the net momentum of the system has to still be zero, because no forces came from outside the system. So therefore, and we know that the cannon will go one way, the cannonball will go the other way. So therefore, the momentum of the cannon has to be equal and opposite to the momentum of the cannonball. And the mouse in the corner reminds us that mass plays a large part of this. So most of the momentum in a cannonball is actually in its velocity. Most of the momentum in the cannon is in its mass. So the forces between the two objects are equal and opposite. That's Newton's third law. So, and the action-reaction forces are internal, so they don't change the momentum of the cannon system. So once again, the momentum is zero before it's fired. After firing, the net momentum still has to be equal to zero. Momentum is conserved. It's neither gained nor lost. Now, momentum has both direction and magnitude. And whenever we see direction and magnitude, we always think of a vector quantity. The cannonball moves in one direction, therefore the recoiling cannon will have to move in the opposite. The cannon system doesn't gain any momentum. So the momentum of the cannonball and the cannon, and they are moving afterwards, have to be equal in magnitude, opposite in direction. And there's no net force on the system, so there's no net impulse on the system, so there's no net change in the momentum. The momentum before has to equal the momentum after the ball is fired out of the cannon. So this is true for every case. You cannot have a change in the momentum because there's no external force in this case. And this brings up an important word, conserved. In physics, when a quantity does not change, we say that it is conserved. We'll see this with the conservation of momentum and the conservation of energy, and we also haven't really talked about, but there's also conservation of mass. So, stating the law of conservation of momentum, if a system undergoes changes wherein all forces are internal, the net momentum of the system before and after the event is the same. Some examples are atomic nuclei undergoing radioactive decay, which means the nuclei actually split into several pieces and they give off other little particles, and the net momentum of all those particles moving away from each other has to be the same. Cars colliding, here's things coming together, not moving away from each other. And something like a star exploding. So I see we're going to be talking a lot in the future about collisions and explosions. So let's do a little, let's think here. Newton's second law states that if no net force is acted on a system, no acceleration occurs. does it follow that no change in momentum occurs? The answer is yes, because no acceleration means that no change occurs in velocity, and therefore if there's no change in velocity, there's no change in momentum, because momentum is mass times velocity. Another line of reasoning is simply that no net force means there's no net impulse, thus no change in momentum. Remember, impulse is force times time, and if you don't have a force, there is no impulse, and therefore there is no change in momentum. What does the law of conservation of momentum state? The law of conservation of momentum states that in the absence of an external force, the momentum of a system remains unchanged.